Now that we've had some experience in using the mole-to-mole relationships from a chemical equation, we need to make that relationship a little bit more useful by factoring mass into the situation. So earlier on we showed how to calculate the molar mass, and we've seen how the molar mass allows us to go from the mass of a compound in grams to the number of moles of that element or compound. And so if we just combine steps that we learned earlier, being able to go from the mass of a reactant to the moles of a reactant, we can then bridge our units to go from the mass of a reactant to the mass of a product, or vice versa. We could say, I want to make this many grams of a certain product. How many grams of each reactant do we need? And that is ultimately much more useful to us because we don't have a device in the lab that directly measures moles. We have to use mass, or in some cases, volume, to do that. Looking ahead, though, I cannot emphasize enough that in order to use the balanced equation to go from one reagent to another, that is, from a reactant to a product or vice versa, you must use the mole-to-mole relationship. The mass alone is not sufficient. So let's go ahead and take a look at a problem where we start breaking this down using the masses. This first problem I'm going to look at breaks everything down into one step at a time. And then from there we'll see how to combine this into a single problem. So switching over to my notes view here, let's begin by balancing the chemical equation. So we have 1 sodium, 2 chlorines. Over here we only have a single chlorine, so we need to put a 2 in front to balance this out. And now we need to address the sodium. We need 2 sodiums, so we'll put a 2 here. And we're done. If we want, we can add a 1 there. No need to. So before we take this on step by step, let's just read through every step so that we know where we're going. So part A asks how many moles of sodium are there in 15.50 grams of sodium. Part B is going to ask us how do we move from that amount of sodium to a certain amount of sodium chloride. So in other words, if I've got my 15.50 grams of sodium, how many moles of sodium chloride will I end up with? And then finally in part C, I want to know how many grams that is. So this is an extremely common set of calculations in chemistry. We are ultimately going from the grams of sodium to the grams of sodium chloride. That's what we would like to do, but we have to do it in a series of steps. The first and most important thing that I want to emphasize here is this tells us that there are 2 moles of sodium for every 2 moles of sodium chloride. It absolutely does not tell you that 2 grams of sodium make 2 grams of sodium chloride. Why is that? Well, if we look on the periodic table, sodium has a molar mass of 22.99 grams per mole. Sodium chloride, we can just calculate, because sodium is 22.99 plus chlorine is 35.45. You can go to the periodic table to verify that. To give us a total of 58.44 grams per mole. So since these numbers are not the same, we can't say that 1 gram of sodium gives us 1 gram of sodium chloride, any more than we could say 22.99 grams of this is necessarily going to give you 22.99 grams of sodium chloride. It doesn't. It gives you the 58.44 grams according to this relationship. So therefore we have to convert to moles before we can go from grams of one reagent to another. And so let's break this down into steps. So we're starting off here with 15.50 grams of sodium. and we will do our grams to mole conversion. So we saw here that there are 22.99 grams of sodium for every 1 mole of sodium. And putting that into the calculator, 15.5 divided by 22.99 gives us 0.6742. moles. Now we want to know how many moles of sodium chloride we would get. Well, since these numbers are the same, it's a 2-to-2 relationship, we'll see that we're just going to get the exact same answer in part A. So in part B we had 0.6742 moles of sodium. And using the balanced equation here, we can go from 2 moles of sodium to 2 moles of sodium chloride. So the purpose of that was simply to change the unit, because the 2's cancel. So this gives us 0.6742 moles of sodium chloride. And now we can find how many grams this is by just using the molar mass, which we had above. So we have 0.6742 moles of sodium chloride. And we know that 1 mole of sodium chloride has a mass of 58.44 grams. You'll notice that I always use the chemical formulas in these problems because we are specifically referring to 2 different chemicals, sodium and sodium chloride. So putting this into the calculator gives me 39.40 grams. You'll notice we had 4 significant digits throughout in this particular problem. Let's continue to practice. So I'd like to essentially do the same problem that I just did, but in just one step now. So let's write out this problem, and we may need to refer back to the previous page for some values. So we want to know if we have 39.75 grams of sodium, how much sodium chloride will that be produced? Notice I did not really discuss the word excess. I'd like to go back and call your attention to that. Excess means more than enough. And whenever someone says excess about a reagent, what that means is you can essentially ignore it. So we don't have to worry about chlorine. We're saying there is more than enough chlorine. In reality, we would actually have to look at both chemicals, but for now, we're only going to focus on one at a time. So when I see excess chlorine, that's just my instruction to say I don't need to pay attention to chlorine. Okay, so we have 39.75 grams of sodium. So just like we did in the last series of steps, we go from grams to moles first. So we're going to go from grams of sodium to moles of sodium. There are 22.99 grams of sodium in a mole of sodium. So I've just used the atomic weight of sodium. If I stop now, I would have moles of sodium. That was part A from the last problem. Now we'll do part B. I know from the balanced equation that every 2 moles of sodium gives me 2 moles of sodium chloride. So I can cancel out moles of sodium, and I can technically cancel out the 2's as well. And then part C, we want to go from moles of sodium chloride to grams of sodium chloride. So 1 mole of sodium chloride has a mass of 58.44 grams. And the units cancel. And so you'll see here that we were able to go from 39.75 grams of a reagent to the number of grams of sodium chloride. So putting this into the calculator, we have 39.75 divided by 22.99 times 58.44. Gives me 101.0. grams of sodium chloride. Let's look at another problem that's very similar, except this time we are going to be starting with the chlorine, the Cl2, and we're saying that the sodium is in excess, which means we can ignore the sodium. I would still like to find the number of grams of sodium chloride. Let me rewrite the balanced equation here. So we know that every 2 sodiums react with 1 chlorine to give you 2 sodium chloride. So we're starting with grams of chlorine. As before, we need to go from grams to moles, but the molar mass of chlorine is different. On the periodic table, it will tell you that chlorine has a molar mass of 35.45 grams per mole. But chlorine is a diatomic molecule, and that means we need to multiply the molar mass by 2. So 35.45 times 2 would be 70.90 grams per mole. Be very careful when you're dealing with the diatomic elements that you take that step to multiply by 2. It's just like you would do in any other formula. So we can now go from grams of chlorine to moles. There are 70.90 grams of Cl2 chlorine in a mole of chlorine. Now remember, the whole point of that step was so that we could now use the balanced equation to go from moles of chlorine to moles of sodium chloride. This is not a one-to-one relationship. We saw that there was a 1 in front of chlorine. So if we want to go from moles of chlorine to moles of sodium chloride, we see that every 1 mole of chlorine gives you 2 moles of sodium chloride. Going back, let me cancel some units. And if I stopped here, I would know how many moles of sodium chloride I would get. And the last step is the same as in the previous problem. We want to convert from moles of sodium chloride to grams. Going into our calculator, we have 146.7 divided by 70.90 times 2 times 58.44. 58.44. And this gives me 241.837, which would round to 241.8, 4 significant digits. And the unit which is left over is grams of sodium chloride. Let's do a little bit more practice here. How many grams of each reactant do we need if we want to produce 100 grams of sodium chloride? And here I have a rather ridiculous set of 5 significant digits. We're going to be limited to 4 because we've already decided that with the atomic masses on the periodic table that we're limiting those to 4. So how many grams of each reactant? Each reactant means we need 2 answers. We need the answer for sodium, and we need the answer for chlorine. And we're going to be doing this backwards. So we're saying now, I want to make 100 grams. How much of each reactant do I need here? So let's start off with the sodium. So I have 100 grams of sodium chloride. And we've already seen that 58.44 grams of sodium chloride is a mole of sodium chloride. And we now want to go from moles of sodium chloride to moles of sodium. So the balanced equation, which we still have up here, tells us that every 2 moles of sodium chloride requires 2 moles of sodium. And we know that 1 mole of sodium has a mass of 22.99 grams of sodium. So canceling units, and we can cancel these 2's here. We can go ahead and figure out how much sodium we're going to need. So we have 100 divided by 58.44 times 22.99 gives me 39.34 grams. I'm limited by the 4 significant digits of the molar masses here. So 39.34 grams. Of sodium. What about the chlorine? We're going to essentially be doing the same first part of the calculation here. So I'm going to be a bit lazy and just say, why would I want to rewrite that? Let's just take it and reuse those numbers. So we're going from grams of sodium chloride to moles of sodium chloride, same first step. And we want to go now from moles of sodium chloride, this time to moles of chlorine. Looking at the balanced equation, we see that every 2 moles of sodium chloride requires 1 mole of chlorine. And then going back and looking at our numbers, we see that 1 mole of chlorine, Cl2, has a mass of 70.90 grams of chlorine. So I have 100 divided by 58.44 divided by 2 times 70.90. And this gives me 60.66. Now you might have noticed that if I had instead just started here and said, okay, I've got 100 grams of sodium chloride, and after the first part of the equation, I have 39.34 grams of sodium, what do we find if I subtract that? Well, we would get 60.66. That's exactly the same number as we got there. This doesn't always work, incidentally, but why does it work in this kind of a scenario? Remember the law of conservation of mass. The chemical equation said that for every 2 moles of sodium, we need 1 mole of chlorine to make 2 moles of sodium chloride. All the chemicals that we see here, sodium and chlorine, only end up in one place. They all end up in the sodium chloride. So it should make sense that the sodium plus the chlorine's masses has to equal the mass of sodium chloride. If that weren't the case, you would be violating the law of conservation of mass. So whatever mass you start with has to end up in the final product. Now, if there were excess of either of these, then this might not seem to work because ultimately it would remain unreacted. So if I took, for example, 2 moles of sodium, and say I added, instead of 1 mole of chlorine, let's say I added 3 moles of chlorine, it would still react to make 2 moles of sodium chloride, but I would just have leftover chlorine. Let's take a look at one more problem here. And the nice thing about this problem is that it will allow us to review some important concepts like density. So let's say we have this question here. So this is going to be ethanol, and we want to react it with oxygen. It's going to make carbon dioxide and water. So let's balance. So I've got 2 carbons here, so I'm going to put a 2 here. I have 6 hydrogens, so I need 2 times 3 there. And now I want to balance oxygen last because it's the only free element. So I have 1 plus 2, I have 3 here. That's not going to be enough because on this side I have 2 times 2, or 4 plus 3. I have 7 oxygens on the right. Over here I have 1 plus, if I want to get to 7, that needs to be 6, right? 1 plus 6. So how do I make this 6? I put a 3 in front. And if I'd like, I can write a 1 in front of the ethanol. So let's go ahead here and carry out a calculation with this. So here's another calculation which has 2 chemicals in it, so it's 2 parts. I want to know how much carbon dioxide and how much water I can produce if I'm using 55 milliliters of ethanol. So remember, we want to get to moles. And at this point, we don't know any way of getting from milliliters to moles. But we do know how to get from milliliters to grams. And we can do that using the density. And then the rest of the problem is the same as before. We can go from grams of whichever chemical we're interested in to moles. And that's what we're going to do here. So we need two chemicals. We're going to need to start with carbon dioxide. So I'd like to produce carbon dioxide. I'm using 55 milliliters of ethane, C2H6O. When using the density, it is critical that you pay careful attention to the units. So the density is 0.789 grams per milliliter, which means for every 1 milliliter. So down here in the denominator, I have milliliters of ethanol, and we said per 1, and this is 0.789 grams. The rest is just like the previous problem. We first go from grams to moles. So I don't know that number off the top of my head. However, I do know carbon's atomic weight and hydrogen's and oxygen. So please follow along with me using a periodic table. Carbon's atomic weight is 12.01 times 2, because there are 2 in the formula. And then for the hydrogens, we have 1.008 times 6. And then oxygen has an atomic weight of only 16, and there's only 1 of them. So I don't need to multiply by anything. And this gives me a molar mass of 46.07 grams. That is 1 mole. Make sure you do that calculation and verify it. Now we want to do what? We were trying to get to carbon dioxide here. So we simply go ahead and say, well, every 1 mole of ethanol makes 2 moles of carbon dioxide. And we finally wanted grams. So we have to, again, go to our calculator to calculate this. Actually, we did this earlier in the notes, and you might recall that a mole of carbon dioxide has a mass of 44.01 grams. Okay, so looking at the calculator, we have 55 times 0.789 divided by 46.07 times 2 times 44.01. And I'm going very slowly through this because I would like you to be practicing entering these into the calculator so you're not making mistakes when you get to exams. And when I do this, I get 82.909, but we only have 3 significant digits, so that would be 82.9 grams. We also want to do this for water. And at this point, I could start with milliliters, or I could start with the grams of carbon dioxide, because as I've said before, we only need to know the amount of one chemical to find out the amounts of the others. I'm going to, again, do my lazy trick here of just copying. Because we're starting with milliliters, I'll need to go to grams. I'll need to convert to moles. So all of that needs to be done again anyway. So let me just bring that down. except that the 1 didn't want to come down with me. So there it is. And this time, instead of going to carbon dioxide, we're going to go to water. So looking at the balanced equation, 1 mole of ethanol makes 3 moles of water. And we want to convert that to grams. So 1 mole of water has a mass of 18.02 grams. I don't recall if we calculated that before. I think we might have. If not, it would not hurt to calculate that again. And so now we have a fair amount of numbers to put in the calculator. We have 55 times 0.789 divided by 46.07 times 3 times 18.02. And this gives me 50.9. grams of water. So that is what we expect. This is very much just like a recipe. This is how much the given chemical is reacting. I did not mention the oxygen, which could have been a bit of a problem here. I did not say specifically excess oxygen. However, I think it should make sense to us that if we are reacting something in the air, there is plenty of oxygen. It's not going to run out. So we have plenty of oxygen there. It's in excess. And I finally want to ask, how many carbon dioxide molecules are there in this sample? This is where we get to use Avogadro's number again. When we want to know the number of atoms or molecules, that's where we're going to go to Avogadro's number. So we had 82.9 grams of carbon dioxide. If we want to find molecules, we first need to get this to moles. So we're just going to work backwards through the original problem here. So we know that there are 44.01 grams of carbon dioxide in a mole of carbon dioxide. And now that we have moles, we can use the definition of the mole for Avogadro's number. Make sure that you always put a 1 with the moles. Avogadro's number never goes in front of moles unless you wanted a mole of moles, which I can't think of would ever need. So a mole of something is 6.02 times 10 to the 23rd of that thing. And carbon dioxide comes in units of molecules. Molecules, not mole, molecules. All right, let's just cancel the units. And we're going to get a huge number. That's to be expected whenever we're asking how many atoms or how many molecules in any sample that would be a size that we could see. So we have 82.9 divided by 44.01 times Avogadro's number, 6.02. I'll hit my exponential notation button, and then 23. And this gives me 1.13, and then look at the end, times 10 to the 24. And that would be molecules. Now, as this is a fairly long video, I'm going to go ahead and end this here instead of continuing on. But these problems are all very much worth putting quite a bit of time into. you'll notice that once you find the pattern, specifically the pattern here of going from grams to moles of something else to grams, you'll see that they almost all have that in common, these problems. Sometimes we have to append an extra step on front or on the back when we try to go to molecules or anything like that. But ultimately, they all are going to have these same series of steps in the middle. So I'm ending this video here, and when I come back, we're going to go in a different direction that's less mathematical and more conceptual in talking about chemical reactions. Thank you.